So we're back to our example problem, what's called the potential divider problem. And from the potential divider, what I'd like to have is I'd like to have an expression that relates V out to V in. In other words, I'd like something of the form that says V out equals V in times something. That's the expression I'm looking for. Okay. Now there's a few things that we already know. We can see directly from the circuit here that V in, according to Ohm's law, must be equal to I've got to use little I here, but I'll go back to big I here, must be equal to the current times resistor 1 plus resistor 2. Remember, no current actually flows through the, sorry, move the thing down a bit, actually flows out of here because the voltmeter has a very, very, very high impedance. So this is actually open circuit here. Okay, so we have V in is equal to I times R1 plus R2. That's fairly obvious. V equals I times R. Well, R is R1 plus R2. We can apply the same kind of reasoning for V out. So what we can say is that V out is actually equal to whatever current's flowing through here times R1 according to Ohm's law. In other words, the volt drop across 2, but so I times R here, but R2 will give us V out. So it's I times R2. It's getting quite interesting now, isn't it? I think you can see roughly where I'm heading on this. So the volt drop across here is V out is the volt drop across here. Well, it's just the current and the resistance together in Ohm's law. And the volt drop across here is the current, but bear in mind this time that the current has to flow through two resistors, so it's R1 plus R2. So remember what we were looking for in the first place. V out equals V in times something. Well, that's fine, but let's just do something really silly now and just say, well, actually let's find V out divided by V in. Okay, just for the sake of argument. Well, if I put V out on the top, which is I times R2, and I put V in on the bottom, which is I times R1 plus R2, okay, I's cancel. V out over V in is equal to R2 upon R1 plus R2, or the form that we wanted, which is that V out equals V in R2 upon R1 plus R2. So that means we now have a general formula which for any pair of resistances in this kind of shape, what's called a potential divider, we can work out how much or how many volts are dropped across here and how many volts are dropped across here. In other words, we can tailor this point here, or V out, to be any value that we want. Within reason, it's obviously got to be less than V in, but it means that we've got a very accurate way of controlling the voltage output of that circuit. Now, you would be absolutely amazed how often potential dividers come into circuits, because okay, these are passive devices, but it's perfectly possible to have other devices in there, and well, just as a simple introduction, imagine if this were a capacitor or an inductor, and that's where we'll be going a little bit later on. But that potential divider, that's where it comes from. I remember when I first saw this, I just remembered the formula, but it's quite nice to know where it came from, and it's just a very, very simple piece of algebra to arrive at it, and a bit of logic attached to it as well. So V out equals V in R2 upon R1 plus R2, and that's going to have massive implications for some very complicated circuits later. Okay, I hope that was useful. Obviously this is on video, so you can come back and look at it again in the future at your leisure. Okay, there's no exams, remember, so you don't need to remember it, it's just for your understanding. Okay, thanks for listening.